Hey everybody, it's Ripley, back again. We're in 6.5. We're in Applications of Physics and Engineering. This is Section Zilla, man. There's so much to do in this section. We're going to take a lot of time on it, though. I think we take 4 days or something like that. This is going to be a relatively long lecture. I'll try and get you through it as painlessly as possible. We're going to do Applications to Physics and Engineering. Okay, so what we're going to need first is we're going to need some basics. The first thing that we need to talk about is we're going to talk about force, okay, and we're going to talk about work. All right, we'll just cover these two topics really quickly. All right, so what we need to talk about is what do they equal first and foremost? Well, we know that force is equal to mass times acceleration. We also know that work is equal to force times distance, right? Hopefully you've seen this before. If you haven't, well, now you know. Now, but let's change colors here and let's talk about units. All right, so we're going to put units right here. So just to, again, this is going to be a review for a lot of you guys, but the units for force are either newtons, and let's see, remember what a newton is? A newton is a kilogram times a meter per second squared. So think about it. Mass in metrics is a kilogram, all right, for this. The acceleration is meters per second squared, so when I multiply them together, I get kilogram meters per second squared. This is in metrics. In the English system of weights and measures, it's not going to be newtons, it's going to be pounds. All right, so just LBS. All right, now this drives physicists insane because if you think about it, your mass on the moon is exactly the same as your mass here. It's kind of how much you displace more. That's more density, but you can think about that. Your mass is the same. The acceleration of gravity is what changes the force that you exert on things, right? I mean, if I'm on the moon and I jump straight up and I land down, the force that I exert on the moon is less because the acceleration of gravity is less. Okay, so this newtons good. All right, pounds bad. But remember, pounds include the acceleration of gravity. There's no way to parse out the acceleration of gravity. I weigh 165 pounds on Earth. Okay, 165, 170. It's getting close on Christmas season, so I go a little chunky. But my mass in terms of kilograms is different. Okay, in terms of the force that I exert on the earth, or that my body exerts, is different. Okay, my kilograms, I don't know what my kilograms would be, something around 70 kilograms, but my force is measured not in pounds, but in newtons. Okay, for work, it's a newton meter, which is equal to kilogram meters squared per second squared, and the word that we use for this is a joule. And the unit is a J. All right. Now this is in metrics. In the English system of weights and measures, it's a foot-pound. Now I used to gripe and moan, so it's foot-pound. You'll see it written as a dash, but really it's a product, because if the force is in pounds and the distance is in feet, then the unit is a foot-pound. All right. So these guys, we like these guys whenever possible, although we have to make sure that we know which system that we're talking about here, because we are going to have to be able to use both systems. Okay, so just remember when you're looking at a unit of force and when you're looking at a unit of work. Okay, now, so we got our units and we got our equations, nothing to it. Now let's talk really quickly about Hooke's law. What we're going to do is we're just going to sort of take a little survey here through, was it Thomas Hooke? I forget what his name was. Hooke's law. We're gonna take a survey through a lot of the main points in physics. So for those of you that haven't had a physics with calculus yet, this is going to be really useful when you finally do, and it'll help you out in future physics class as well. Hooke's law is really simple. It simply says, all right, given a spring, all right. So let's say that this is a spring in its natural position. If I stretch this thing out, all right, what does that take? It takes force. It also takes work, right? It's going to take some work to be able to do this, if you think about it. But what Hooke's law says is, it says that the amount of force that it takes, let's use capital F so I can be consistent, the amount of force that it takes to hold a spring at a certain stretched value is proportional to the distance that we are from its natural length. Now, you got to think about this. You can either compress a string or you can stretch a spring, right? If you think about compressing strings, those would be like the springs in the shocks of your vehicle versus just a regular old, spring that you would pull out of your ballpoint pen. All right, so this distance right here is x, and it kind of makes sense, right? The farther that I stretch my spring until it blows out, it loses that spring constant. The farther that I stretch my spring, the more force it's going to require for me to be able to hold it there. Okay. Now, I'm going to come up with a problem, and it's a great problem because it makes us really kind of play with this thing. All right, we're going to do this whole thing. We're going to use integrals to be able to solve some pretty intriguing problems. Okay, so let's come up with an interesting problem here. Let's say it requires, or it takes, let's say 20 newtons to hold a spring 10 centimeters from its natural length. Natural length. Okay? How much work is required, to stretch it, from 10 centimeters to, let's say, 15 centimeters. All right? Now, let's go nice and easy here. We're going to use Hooke's law. We're going to figure this thing out. The first thing that we need to acknowledge here is we've got an equation here with three unknowns. We got force, we got some sort of constant, and then we've got a distance. Okay, so let's see what we can figure out, and then we're going to have to answer a work question here. So what does it say? It says 20 newtons, so I know that's a measure of force. So I know that if I take F equals kx, then I know 20 newtons is equal to, now what else do I know? I know that this spring is being stretched so that x is 10 centimeters past its natural length, right? So I'm stretching this thing 10 centimeters, what about? A little over 5 inches, more or less. All right, 20 newtons to hold it there, not to stretch it through, but to hold it at 10 centimeters past its natural length. So I can solve for k. You always want to be able to solve for k with these things one way or the other. All right, so k times 10. So it appears, let's actually put some units on here. Is it k times 10? Because this is centimeters, but let's look at the units on newtons. That has to be in meters, doesn't it? So I need to change this into meters, and you got to be really careful with this. So this is going to be k times 0.1, right? 0.1, because it's 1 centimeter is 1/100th of a meter, so 10 centimeters is going to be 0.1 meters. All right? So what does that imply? Well, it implies that k is equal to 200. Now, what are the units on k? Well, it's kilograms per second squared, isn't it? If you do the dimensional analysis, it's really easy to figure out what the units are on these things. I'm dividing out. Let me show this. Let me change colors. All right. I've got 20 newtons, which is 20 kilogram meters per second squared. If I cross out my meters, I'm left with kilograms per second squared. Okay, so I know that in general, the amount of force required to hold this spring at any distance from its natural length is 200x. All right, we can play with the units later. The question is how much work is it required to stretch from 10 centimeters past to 15 centimeters? Well, let's think about that. All right, so here's what I'm going to do. I've got my spring. Let's make a little diagram, right? And then I'm stretching this guy right here. Now, let's say that this distance right here is 10 centimeters, and this distance right here is, what I say, 15 centimeters? Clearly not drawn to scale. Now, as we're stretching it through from 10 centimeters to 15 centimeters, here's what I'm going to do. I'm going to take a little chunk right here, and I'm going to call, we've seen this before, right? This is going to be my action. I'm going to figure out how much work it takes me for this little ith bit of action. Now, you can probably already feel where this is going based on what we've already done. This distance from here to here is going to be x sub I, correct? Now, what are we doing? We're taking a force. I mean, think about what it means to stretch a spring. You're basically holding a spring, and then you're adding in a little bit of distance at a time, an infinitely thin amount of distance, and then you're adding it up. Well, do we have a tool by which we can add up an infinite number of infinitely thin little distances? Yeah, of course, right? That's the integral. So if I look at this little guy, this little sliver of work that I'm going to do, then this chunk, I probably should have drawn this a little bit bigger, it's just going to be delta x, isn't it? And delta x is the distance through which I've stretched my spring. So that distance gives me this distance from over here in my equation. So watch how this works. I'm going to do a couple of things. I know that the force required to hold the spring at any one of the intermediate distances between 10 and 15 centimeters is 200 x sub I. I know that the work required to get it from 10, or excuse me, through that little delta x is 200 x sub I, that's the force, times delta x, right? Now, that's the work done for the ith little sliver of action, right? Or this little interval right here. What is the overall work? Well, I'm going to add up an infinite number of infinitely thin slices of work. So here we go. I'm going to integrate 200 x times dx, right? Delta x is turned into dx's and x sub I is turned into x's. Now, think about this. Where is the action taking place from and to? We got a little sliver of action here, a little sliver of action here, here, here. I started at 10 centimeters past its natural length, right? All right, easy enough. So I'm starting at 10 centimeters. So my action goes from 10 centimeters to 15 centimeters. Oh, but wait, there's another trap. Remember, these have to be in terms of meters because the units on both of these are meters and not centimeters. So this goes from 0.1 to 0.15. Easiest thing in the whole wide world, right? This turns into what? 100x squared, integrated from 0.1 to 0.15, which is, oh good God, let's see 100 times 0.15 squared minus 100 times 0.1 squared, right? And whatever the heck that is, let's pull out our calculator. Hey, I happen to have a calculator right here. Let's have a little fun. So I'm going to do 100 times 0.15 squared minus 100 times 0.1 squared. I wish I could do those quickly in my head. I suppose I could have a little bit of work. And I get 1.25 joules. So this appears, because the units of work are joules. So what did I say? 1.25? 0.25 joules. Now, I'm also going to use my FNINT to double check this. Your calculator is a wonderful tool on this. I'm going to do FNINT, and I'm going to go from 0.1 to 0.15, 0.15, and then I'm going to do what? 200x, 200x, and then dx. We'll see what we get. You can always check your work, which is lovely. And oh, we did it right. Isn't that cool? All right, let me do one more for you. It's just it's a little bit tricky, so we'll do one more of these guys and see what happens, because I want you to see kind of how tricky the Hooke's Laws problems can be.